My name is Daniel Berlyne, and I'm going to be talking about graph braid groups today. And for those of you who aren't familiar with what a graph braid group is, what I want you to have in mind is this classical picture of a braid, which is simply n strands intertwined with each other by a sequence of half twists. So, for example, a 3 braid might look something like this. And then what I want you to do is embed this, this braid in a copy of the cylinder, so D2 cross I. And then what I want you to do is start taking cross sections of this cylinder, as so. So what you're going to see is you're going to see copies of the disk with n marked points corresponding to the n strands of the braid. And as you move down through the cylinder, you can see these marked points moving around the disk as you pass along your braid. So you can kind of think of this like a movie where the vertical direction represents time, and each cross section is like a snapshot in time where you see your particles, your marked points on the disk as they're moving around. So with this interpretation in mind, an n braid is simply n particles moving around the disk without colliding with each other because the strands of the braid don't intersect, and then eventually returning to their start locations, potentially with some of them permuted with each other along the way. Okay, so one reason why this is a nice way to consider a braid is that it's quite easy to generalize. We can simply replace the base space, the disk, with any other space we like. So in our case, we're going to be taking X to be a finite connected graph. And one useful tool in this model of a braid is something called the configuration space, which is simply the space of all possible configurations of the n particles on your space X. So you take n tuples of points in X such that no two of the points are the same. Again, because the strands of the braid don't intersect. So in terms of the configuration space, an n braid is simply a loop in Cn of X. And then the next obvious step is to try taking the fundamental group of this thing. And this gives us our braid group. Now, technically, if you take the fundamental group of the configuration space, this gives you the pure braid group. What we want to do is first quotient the configuration space by the action of the symmetric group on the coordinates of x to the n. And this gives us the unordered configuration space. So in other words, we don't want to distinguish between the different strands of the braid. So then the fundamental group of this gives us the braid group that we want. All right, so again, we're taking X to be a finite graph. And the reason we're so interested in this case is because of this beautiful theorem of Abrams and Crisp-Weist, which tells us that if X is a finite graph, then the unordered configuration space actually deformation retracts onto a compact special cube complex. And as geometric group theorists, this makes us very excited. It means we can apply all of our wonderful theory of cube complexes. And among other things, it implies that graph braid groups are hierarchically hyperbolic groups due to a theorem of Bairstock, Hagen, and Sisto. So briefly, hierarchical hyperbolicity is a generalization of Gromov hyperbolicity. It was developed by Bairstock, Hagen, and Sisto as a way of axiomatizing Mason-Minsky's treatment of mapping class groups using curve graphs and subsurface projections and so forth. So we have analogs of all those tools. And among other things, it allows us to characterize when a hierarchically hyperbolic group exhibits other forms of hyperbolicity. So we can characterize when these groups are hyperbolic, when they're acylindrically hyperbolic, and when they're relatively hyperbolic, where these characterizations are in terms of the hierarchically hyperbolic structure. So in particular, by developing an explicit hierarchically hyperbolic structure for graph braid groups, I was able to characterize when graph braid groups exhibit these three forms of hyperbolicity. And so the first two are were already shown by Genevois, so it allows me to recover those theorems via an alternative method of proof. And then in the third case, the result is new. So, so the characterization of hyperbolicity looks something like this. We need to split it into 4 cases, depending how many particles you have. Basically, the reason for this is that we're looking for copies of Z squared in our group. And now copies of Z are generated by cycles in the graph gamma or stars in the graph gamma. However, in order for a star to generate a copy of Z, you need at least 2 particles, right? So that's why this gives us this condition on the number of particles. And then disjointness tells us that you have a direct product. Okay, so in the fourth case, for example, the graph would have to look like something like this. You'd have one central vertex, a number of loops coming out, and then a number of edges coming out. And that's what the hyperbolic graphs look like. I also provide a new proof of a characterization of acylindrical hyperbolicity, which basically says all graph braid groups are acylindrically hyperbolic unless they're cyclic. And then I have a similar characterization of relative hyperbolicity. Now this one I've labeled as a theorem / conjecture because technically there's still a little bit that needs to be done to complete the proof of this, but I do have an explicit characterization. And I'll give you a brief description of how that goes. So what we're doing is we're trying to look at pairs of disjoint subgraphs of gamma, each of which contain a star or cycle. And then we're trying to chain these together in such a way that we cover the whole of the graph gamma. So by taking this, a union of 2 disjoint subgraphs, this gives us a direct product subgroup of the graph braid group if you take the braid group on that subgraph. And then we want the intersections of successive pairs to contain a star or cycle so that the corresponding subgroups have infinite intersection. Then if this covers the whole of gamma, then this implies that Bn of gamma is thick, which is an obstruction to relative hyperbolicity. Okay, and then otherwise, if we can take maximal chains and isolate them, then this gives us relative hyperbolicity, where the peripheral subgroups are given by the groups generated by these maximal chains. Okay, so I've simplified things a lot, but I'm going to leave that there. Thank you very much.